on number 1 here. And this is a problem that I don't think that I've ever done anything exactly like this. I've done several things that were similar to this, certainly. So you want to kind of write down these notes as we do this, because this is pretty important. So with this one, what you're given, you're basically given this. You're given a of t, and that's an acceleration. We did talk about, oh, it would help if I'm displaying. Is that what you're trying to say? Okay, all right. Okay, all right, very good. Okay, so we have the acceleration is negative 9.8 meters per second squared. Okay, and then we've got, and then basically what's happening on this, you have kind of some object, and it's rising. That object's rising. And at some point in time, it's going to be 200 meters above the ground. And let's see, the other thing it says is, right now, at this instant, when it's getting to this point here, and it's saying the velocity is 20 meters per second. I just made this problem up, so the numbers are going to work out weird, probably with quadratic formula or something like that with decimals and stuff. Okay, so we got that, so it's rising upwards, and then what it says is, the question is, in how many seconds will the object reach the ground? Okay, well, let's talk about this then. Okay, now I've given you the background information to solve this, but I don't know. If I threw this out there, I wonder how many people would be able to solve this. What do you think at first glance?
It's y equals 0, right?
Well, that's something to do with that. What you're doing is you're doing integrals. A couple of things that you want to review first of all before I do anything with this problem, and I'm just going to kind of write this down as a little sideline review here. Okay, so first of all, S of t usually represents the position, and you can write this information down if you need to. S of t is a position, and v of t, of course, is the velocity, and then a of t, of course, is the acceleration. All right, well, it goes like this, and we haven't done this in a long time. Gosh, I can't speak and write at the same time sometimes on this thing. If you want to take one of those. All right, so just as a kind of a sideline review here, okay? And you may write this down if you want to, but you don't necessarily have to. Let's just say that your position was, let's say, 32t squared plus 20t minus 15, okay? Typically a position function, not always, but typically is quadratic a lot of times. How do you find the velocity? You do the first derivative. Now, that's something you want to make sure that you know. So the velocity, what it is it's the first derivative of whatever the position function is. And this position function, so that would be just 64t plus 20, like that. How do you find the acceleration? You do the second derivative, right? So you do the derivative again. So the acceleration is really just the derivative of the velocity. And in that case, that would be 64. Okay, that's the background information you got to know to understand this problem. And what we're doing is we're going in reverse on this problem. Okay, so when we go in reverse with derivatives, what are we doing? We're doing integrals. Okay, whenever we reverse that process, we're doing integrals. So the way this problem would start off is kind of like this, and this is the whole key on this. You set up what's called an initial condition problem. And we've talked about initial condition problems. You even had one of these, I think, on your third exam. That's just if you're given a derivative and you're finding the function where it came from. In a sense, that's what you're doing. So what you would have on this is, really you would have this. You have, what's going to happen on this object is it's going to rise to 200 meters, and then at that instant, it's going to drop something to the earth. Okay, it's kind of like, it reminds me of those guys that were doing the class where you had the balloon rising. Okay, it's the balloon or whatever's rising. At some point in time, you drop an object, and then you can figure out how long it's going to take that to reach the earth. So the idea on this is I gave you this information. We're going to go ahead and say t equals 0, because what we're going to say is once that balloon or whatever that object is reaches 200 meters, that's when we're going to time it when it drops that rock to the earth. So we're going to start with t equals 0, okay? And then what you're given on this is you're given the velocity at 0 is 32. Okay, or was it 32 or what? No, it was 20 on the problem I gave you. It's 20. So you were given this velocity is 20 meters at that instant in time. Okay, so that's what you have. Now the other thing you have is the derivative. What is the derivative of the velocity anyway? That's the acceleration, right? And I gave you the acceleration like this. Now the key to doing this problem is to write that stuff down right there. That's what you call an initial condition problem, and we have enough information to solve this problem. And if you're doing an initial condition problem, this is what you have to have. You have to have a derivative of some function and an initial condition. This just means when at 0 seconds, that the velocity is 20. That is your initial condition problem. If you don't set that up, you got no prayer of getting this right. Now the rest of this is integration, so it's not that hard. Now tell me if that makes sense what I'm doing. Weird looks, yeah. You okay? Okay. Now I'm letting t equal 0 just because that's when it's going to drop the rock, and then we're going to time it from there. Okay. Now what we're going to need to do on this is we're going to need to find the position function. Okay. So first of all, what you want to do on this is an acceleration. The first thing you got to do is you got to find the velocity. Okay. How do you find the velocity if you know the acceleration? We're going backwards. So what do? You integrate, right? So what you're going to do is you're going to do the integral of that acceleration, which is negative 9.8 dt. Okay? Now the integral's on this. The mathematics behind this is pretty easy. What's the antiderivative of negative 9.8? Negative 9.8. Then what else? Plus c. Okay? You got to have the t plus c. Right? Okay? That's it. That's step 1. Okay, now step 2 is you got to find c. Okay, how do you find c? Well, I gave you this initial condition. If t is equal to 0, which it is, then this is equal to 20, right? So what you're going to have is you're going to have an equation. So right now what you have is v of t is equal to negative 9.8 t plus c. Okay, when t is 0, which I'm going to replace that t with 0, then that velocity is 20. Okay, so in your head, what's c? 20, right? Okay, so we got that. So we have c is equal to 20. So what we've accomplished is we have this. We have v of t. It's the integral of negative 9.8, so it's really negative 9.8 t plus 20. Okay, that's result number 1. What you ultimately have to do is get the height of the object. You got to get s of t, because s of t, we're going to figure out when s of t is 0, because that's when it drops to the ground. Okay, like that. Are you guys with me so far? Okay. Now the integration's not hard. The calculus is not hard on this. It's just the concept behind this is a little challenging. All right. If you know the velocity, how do you find the position?
Take the integral.
You do the integral again, right? Okay, remember, everything's going in reverse, okay? So that's kind of like step 1 is to get your velocity. Step 2 is to find the position. So we're going to find s of t, okay? So the way to find s of t is to do this. You would say s of t is equal to the integral of negative 9.8 t plus 20 times dt. Okay, and that's going to be the whole key to this, to getting this problem figured out then, okay? So then what we'll have on this is, okay, that integral should be pretty simple. That's going to be negative 9.8, and then what do you do with the t? T squared over 2, power rule. And how about the integral of 20? 20t. Then you have plus c like that, okay? Now, the other thing that you have is this. Now, you got to figure out c. There is enough information to find c on this problem. And basically what you have is s of 0 is equal to 200. Okay? When that object releases this rock, that's when time is 0 and you're 200 feet above. Okay? Or 200 meters, I guess, is what that is. So what that means is you're going to plug this in. Everywhere you see a t, put in a 0, because that's when t is equal to 0. and then plug in a 200 there. Now, you can do this C in your head. It's easy enough to do in your head. That would just be 200. And let's see, if you take this, what is that, like 4.9? Is that what that is? I don't need my calculator. That's negative 4.9 t to the second. And hold on, that's good. You're going to plug in a 0, but I'm going to write this down just so you can see how you can do this in your head. That would be 0 to the second plus 20 times 0 plus c. All right, so what's c? 200, okay? You can bypass that if you can do that in your head. Okay. Now, so what we've accomplished on this is we've accomplished this. We have s of t is equal to, it looks like we have with our antiderivative, we have negative 4.9 t squared plus 20t, and then we have c is 200. Okay, that's what we've accomplished so far in the problem, and that's what we're trying to accomplish is get that. All right, you guys understand what I'm doing? How many people think you would know how to do this problem out of curiosity? You're kind of maybe over there? Halfway, sort of. To me, if you don't know how to start this problem, you won't get anywhere at all. Okay? Because the thing that students usually have trouble with on this is the finding C part. Yes?
I guess one question I have is, as you keep integrating backwards, like that C keeps getting filled in, you keep adding a new C to it, which is why you see the C disappear at 20 seconds. Right?
Yeah, you got to have enough information. I have to give you the height. That helps you find C. And I also have to give you the velocity, the exact value of the velocity. That helps you get C. Because if you can't get C, you won't be able to figure this out. Okay? Now, here's the last part of the problem. Here's how you finish this up. Okay, so now the question is, when does whatever that object is, like the rock, reach the ground? Okay, now we've done this before. Okay, so what do? We're almost done. We've got one more key thing. You just set that function equal to 0, because remember, s is a height. That's a height. So when you're at the ground, the height is 0, okay? So what you would do with this then is you would have 0 equals negative 4.9 t squared plus 20t plus 200 like this, okay? Now what you have to do on this then is you'd have to go to the quadratic formula to figure this out then, okay? So what we would do here is we're going to do quadratic formula. So we're going to go negative b is 20, so that's negative 20, plus or minus square root of b squared, negative 4.9 squared, minus 4ac, so a is negative 4.9, c is 200, and that's all over 2a like that, okay? Now you're going to have a problem very similar to this, but I'll tell you this, the numbers are going to be a little easier. Okay, because I think what you're going to see on your final is going to factor, because it's on the non-calculator part of the final. So it better factor. I haven't worked the problem out yet, but I suspect it does. Okay, all right. So from here, what you do is I'm just going to kind of use my calculator and get what's under the radical on here. So I'm just going to do 4.9 squared minus 4 times 4.9. Hold on, that would be a plus. So it'd be 4.9 squared plus 4 times 4.9 times 200. Okay, you can write this down if you want to. So that would be negative 20 plus or minus square root of 3,944.01. And then the bottom will be back to negative 9.8, like that. Okay, and I'm going to do the square root. And by the way, if the problem you see, if you can't factor it, well, you can still use quadratic formula, okay, and then it should be able to get it fine from that point then. Okay, so let's see. This is what you would end up doing, and what you'll end up doing on this is you'll get one answer that makes sense and one answer that does not make sense. So you would have negative 20 plus 62.8 over negative 9.8, okay? That one right there does not make sense. Do you know why? Just by looking at it. Because it's a negative answer, right? Okay, and I'm not even going to bother with this. It's just, okay, the numerator's positive, denominator's negative. Negative time, that's nonsense, right? So the other one is going to be the right one. You would have negative 20 minus 62.8 over negative 9.8. So that's going to be negative 82.8 over negative 9.8. That'll give you the answer. Okay, so that takes about 8.4 seconds for that to happen. Okay, all right, study that problem hard. Okay, I looked at that problem and I thought, I don't know how many people would know how to do that. Okay, that's kind of my thought. I mean, usually, and I've seen problems like this in the past without giving a little help on this, students get about halfway through it and then kind of get lost with the constant c. Okay, has everybody got that down? Okay, all right, and you'll see something very similar to this, and the thing is, I think the numbers will be easier. I just kind of picked some different numbers that made sense to me. Negative 9.8, those of you who have been in physics or something, is the acceleration due to gravity. In feet per second, it's negative 32 feet per second. Okay, so that's how that goes. Okay, all right, so be sure that you go through that and see if you can do it. Okay, the other thing that is not on my review that you want to make sure that you know how to do is, and we've done this before, I just didn't put this on my review, is you're given a graph of a derivative. I'm going to take one of those. Okay, you're given a graph of a derivative. And what you want to do is the function. Okay, so you're given the graph of, or you're just given the graph of f prime of x. Okay, and we've done this before, like where I've given a graph of a derivative, you give the function that provided that derivative. Another thing you did a lot was I gave you a function, you graphed the derivative. Now we're kind of doing this in reverse. So let me show you a couple of approaches to this to these problems then. So this one right here, I'm going to just kind of get the key stuff on here. It looks like at negative 2 you have an x-intercept, and that looks at like at 4 you have a y-intercept like that. Now this is a derivative, okay? Now you could actually find the specific graph of this now that you know how to integrate. You could theoretically do this, okay? If you could figure out what that is. But all we're doing is just doing a rough graph of this. Okay, now this is a line, right? Okay, if you do an integral of a line, now what's a line look like? It's x, right? It's got an x in it, right? So I don't know what this is. The graph of this is actually y equals, that slope is up 4 over 2. So it's 4 halves x, and then the y-intercept's 4, so you would get y equals 2x plus 4. Now, if I wanted you to just do a graph of the derivative, just kind of a rough graph of the derivative, well, what would be the antiderivative? If you have x, what's the antiderivative of just x? X squared over 2, which is what kind of graph? It's a parabola, right? Okay, so we're going to expect our graph to be a parabola. Okay, so you could actually, like I say, you could figure it out perfectly if you wanted to on this thing, but we know it's going to be a parabola, okay? So the idea with this would be, if you went through and integrated this, you would have this then. So if you did like the integral of 2x plus 4 dx, okay, what you'd end up having on that is the antiderivative would be 2x squared over 2 plus 4x. So that would just be x squared plus 4x like that, okay? Plus c. Yeah, you'd have some kind of a plus c, so you would never be able to figure out that plus c, but all that means is your possible graphs would just be shifted up or down like that. So the idea with this thing is you could go ahead and graph this like this, and you could make a table of values. You could just kind of forget about the c for a minute here. And what you could do here, if you wanted to make a table of values on this, is just kind of choose a few points. So I'm going to do like maybe -2, -1, 0, 1, 2 like that. And then we'll have at least one graph, and then I can show you how all the graphs look. So I'm just going to plug in. You would have -2 squared plus 4 times -2. That's going to be 4 minus 8. So that looks like that would be -4. You plug in a -1, -1 squared plus 4 times -1 would be 1 minus 4, that's -3. Plug in a 0. That would be 0, 0, it looks like. Plug in a 1. That's 1 squared plus 4 times 1. So that is a... I know it's 5, but I'm looking like something seems wrong to me, but I think I'm okay. Okay. All right, so I'm slow sometimes, not that slow. Okay, so we got, the next one would be 2 squared times 4 times 2. So that'd be 4 plus 8. I see what I'm doing. I see why I was thinking I made a mistake in there somewhere, but not. So this would be 8 plus 4, that would be 12. Okay, well, you know, you could plot these points, and that would give you a possible parabola on this. So the idea with this would be, is if you just plotted these points, you would have like -2, -4. You would have -1, -3. I'm going to just kind of write that as -2, -4 like that. So you'd have -2, -4, -1, -3, 0, 0, 1, 5. So if I go over like that's 2, 1, 5 is up there somewhere. That's just kind of giving you like that part of the parabola like that. And then if you did from there, you'd kind of end up having the vertex. So you could have something that looks like that. You could take another point. I'm going to take one more point out like this. If you do -3 squared plus 4 times -2, that's 9 minus 8. So that's also going to be a 4 on that. Okay, or not, no, 9 minus 8 would be 1. So then you could just kind of plot in your parabola like that. Okay, and that would be a possible graph, as it's just a parabola that would end up having, that would end up being the antiderivative of that. Now, remember plus c, what that does is just shifts it up and down kind of. So you could have all kinds of graphs. You could just do this like this and make, you know, as many parabolas as you want to. So the idea is if you're given a graph of a derivative, you're doing an integral to figure out where that comes from. Now that's the idea. That's how you would do a linear function, is like that, is figure out the line. Remember y equals mx plus b. You should be able to figure out the line and then integrate it. Okay, does that make sense to you?
If we see a line on the exam, we just draw the line.
Well, you would know it's a parabola, but you want to be more specific. See, here's the thing. This is what that maybe you hadn't caught on to, is what is the deal with the derivative right there? What's the value of the derivative right there? 0. Okay, does that make sense that the derivative would be 0 at that vertex? Yeah, because see, there's a tangent line there. So you can't just draw any old parabola. Now, you don't have to do this table of values. What you could do is you could realize, okay, derivative is 0 there, so therefore that's where the vertex of the parabola is. And then where you put that parabola, remember you have a plus c, so that doesn't matter what the height of that parabola is. So one way to do this is just to actually figure out that line, like I did there, and actually number crunch. The other way is to know it's a parabola, and to know at that point right there, since the derivative is 0, then that's where the vertex would be. Does that make sense to you?
So you'll accept it if we show no work and just say...
You could actually show no work on this, and you could just draw a parabola. As long as your vertex matches that point there, you should be good. Okay, because it's just a rough sketch anyway. That's the idea. Does that make sense? Okay. Now, if it's a line, if you're given a line, you can figure out the exact antiderivative if you want to. Here's one other illustration here. And this one, again, we're just going to do kind of a rough graph on. So this one I've given a parabola, kind of the key points on here. This is 1, and then 1, 2, 3, 4. Let's see, at -4, you have an x-intercept there. And then the other real key point is at -2. That's the vertex of the parabola, which is -3. So you've got this. Okay, so we've got this parabola going like this. What we're going to do is sketch a derivative. Okay? Now, one way to look at this is a quadratic, right? So quadratic functions are x squared, right? If you do an integral of x squared, what do you get? You get a cubic function. That's all that matters, is a cubic function. Okay, cubic functions typically look like this, or they might, if they reflect, they might look like that. Okay, now what the key thing is This right here is the whole key to the problem right here. It's a cubic function, but those are going to be the places where the derivative is going to be 0, right? Okay. Now what would happen is if you did an integral, you would get the plus c, and you're never going to figure out what plus c is, so your cubic functions can be any height that you want. Does that make sense? Okay, that's what that plus c does. So here's what you're going to do. You're going to draw a cubic, which looks like this. That's a basic cubic function. And if the derivative is equal to 0, well, then what does the graph have to look like when the derivative is 0? The tangent line's got to be this way, right? So you got to draw this graph in such a way that you would end up maybe having a tangent line kind of going something like that. Okay? You would have to have something like that showing that you have a tangent line that's like that. And then you could go down as far as you want to. We're not getting this accurate. The idea would be when you get to that point there, you would also have to level off like that. Okay, and that would be a possibility. There's all kinds of possibilities on this problem. It's just got to be some sort of a cubic function where you have that. The other thing is on this is this. Okay, the derivative right here, that's a positive derivative right there, right? Okay, look at my graph I drew. Is the derivative positive? Okay, my pencil is my tangent line. Is that a positive sloping tangent line? Yes, okay, so that looks good, okay? And then from here you have a negative derivative. Now I'm running into some problems here, so I'm going to have to adjust my graph. So what I'm going to have to do, if I have a negative derivative, what's the graph going to have to do? It's going to have to change direction. So it's going to have to kind of go down like that, and then eventually it's going to have to become positive again. So that's what you have to pay attention to, is that. So one way to do this would be kind of reason this out kind of like this. Okay, now I wasn't paying attention to that and I need to. So what would happen on this is you would have to have a negative derivative like that, and you would have to probably get back to a point where you would have a positive derivative like that. So you would have to probably kind of level off something like that. Okay, whoops, that's not right. I'd still have a negative derivative, so you'd end up doing this kind of thing like this. So you would end up having a negative derivative. Then from there you would have a positive derivative kind of like that. So what you would end up having with this is positive derivative, 0 derivative, negative derivative, okay, 0 derivative, and then positive. So you're going to have some sort of a shape that looks kind of like that. Now how high up you do that doesn't make any difference. Okay, so that's the idea. Okay? Does that make sense? I can't tell. Okay? Now I want to go back to that line problem and look at that just a little bit. The other thing that you want to pay attention to is, if you go back to this problem that I did the line on, the other thing is, with this one, you want to make sure right here you have a positive derivative, or right here on this line you have a negative derivative. So here's the thing here. The parabola is, this is the graph of your derivative. That line's the derivative. And what happens is these are negative values of the derivative, right? Those are all negative values. Is my slope negative right now?
Yeah.
Yes, okay, then it's 0, so that matches that. Now what do you have? Positive values for the line, so it's positive like that. That's what you have to think about. You got to think about when the derivative is 0, when the derivative is positive and negative to draw your graph. Okay, does that make any sense to you? Okay, so just go over that kind of thing. I mean, you can be given graphs of lines, parabolas, things like that, and then you have to be able to sketch the function where that derivative came from. Okay? All right, let's go to some integrals here. Those are two things I think you want to definitely study on there and make sure you're able to put that together okay. On this thing, we've done lots of integrals. At the end of Calc 1, sometimes students are lacking a little experience on some of these things. Now, one thing on the final, we don't tell you if it's U-substitution. Okay, you got to figure out if it's U-substitution. You're going to know it's U-substitution if you don't immediately know the antiderivative. Okay, do you know some function that you would take a derivative of, just like that, that would give you sine the 4th x cosine x? No, it's too complicated. Okay, so if your integral is complicated, start thinking of U-substitution. Okay, because I don't tell you which one is which. Okay, all right. So we have a couple of choices. We could let u be sine. We could let u be sine fourth. We could let u be cosine. There's only one way to make this work out. Any idea? What's that? Just the sine, not the sine to the fourth. See, if you did u equals sine to the fourth, then the derivative would be 4 sine to the third x cosine x. And that's way, way off, isn't it? Okay, what you want to do is you want to let u be just the sine of x only. Okay, and the idea is you would end up with u to the fourth. Do you know how to do the integral of u to the fourth? Yeah. Absolutely. That's u to the fifth over 5, right? Okay, so you like that. Okay, what is du in this problem? Isn't that what you were wanting? Yep, see, that's the idea. Okay, remember when you're doing U-substitution, du needs to match what's left over or only be off by a constant. Okay, so what's your integral going to be now? U to the fourth du, right. Okay, now we're in business. Okay, so what we'd have from here is that would be u to the fifth over 5 plus c. Don't forget you put your plus c's if it's an indefinite integral. And what's the last thing you do? Plug the u back in. So again, the sine goes back in there. So plug the sine into u. So you would end up having sine to the fifth x over 5 plus c. Right? What if you wanted to find out you're right? What would you do? You take the derivative. Okay, so I recommend anytime like on a final exam, if you got a little time, just take the derivative of your answer and see if it's right. You have the power. Okay, yeah.
I was watching a YouTube video last night where they described this where you have du equals cosine x dx. You can solve for dx and then plug it into the original equation for dx, and then those will cancel out. And if they don't, what's remaining is like what your term is you're adjusting by.
Possible. Kind of depends a little bit on the situation. When you get, like when you take Calc 2, you will study this kind of integral more extensively, where you have powers of trig functions, like something to a power. This one can be done by U-substitution. Most of them cannot. So you may have been watching something where you couldn't do it by U-substitution. Okay, does everybody understand what I just did? Okay, yeah. I put the u back in. Okay, so remember u is sine x, so that goes in there. The cosine will not be a part of your answer because everything was accounted for. You just turned it into the u to the fourth integral. So there isn't a cosine in your answer. Okay, and see, notice if you took the derivative of this, if you checked it, you would have 1/5 times 5 sine to the fourth x times cosine x. That would take you back to the beginning. Okay, and that's what you want to do is you want to be sure you check that out. Okay, all right. To me, some of the integrals that I saw on the final, you know, there's some that are U-substitution. Some of them, you gotta think a little bit about identities. Okay, now if you saw something like this, I'd be kind of curious how many students would be able to reason this thing out. Okay. You got to think about trig identities. U-substitution, you're not gonna get anywhere. If you let u be cosine, then du is negative sine x. That's no good. If you let u be cotangent, du would be the derivative of the cotangent, which is negative cosecant squared. Okay? What do you think? Identities. Trig identities is the key. Okay, that's possibly. You could change the cotangent to cosine over sine, but there's something else. I just want to see if you see it. What is 1 over cosine? Secant. What is 1 over cotangent? Tangent. Okay? Okay, 1 over cosine is secant. 1 over cotangent is tangent. Does secant tangent mean anything to you? Ah, that's the derivative of something, isn't it? Okay, that's what you want to do. So what you want to do is you want to change this to 2 secant x tangent x. Sometimes when you're doing integrals, you just do simple stuff like that. Okay? And at this level of Calc 1, there's not a lot of integrals you know how to do. Okay, so you just got to see, okay, is there any way I can manipulate that so I get an antiderivative I know something about? Okay, anyway, what's the answer to this integral? 2 secant x plus c. Okay, you could take the 2 out. You don't have to show that step, but you would do that. Okay, and if you took the derivative and worked with identities, you would get back to the beginning pretty easily. Okay, now your thought over there, I think you were thinking cosine over sine. I suspect that if you played with it more, you would ultimately have to get here anyway. Okay, and you probably would have got there. Okay, so look out for those kind of things. These next two integrals, you know, a lot of times this is such a big deal in Calc 2. You know, if I was writing the final, I probably wouldn't put anything on here because I know Calc 2, this is where this is going to be such a big deal. So I want to see, we have done this before, but I want to just, it seems to me when I was looking at the final, I was thinking, God, I don't know how many students would remember this because we didn't emphasize it very much. Do you guys know what you would do?
Is it arctangent?
Has something to do with arctangent, right? Okay, now what you all learned is that if you had the integral of 1 over 1 plus x squared, okay, what do you take the derivative of that gives 1 over 1 plus x squared?
X.
The arctangent, right? Okay, so this one is like inverse tangent. Okay, now what happens on this then is these are slightly different. You can't do these with U-Substitution. There's a formula for it. I've told you that formula. I taught that formula. We just haven't seen it very often. So what I would suggest that you do is write down this formula and learn how to use it. Okay, and by the way, those who are going to Calc 2, you will do this so much in Calc 2 that you'll have it down. That's the reason if I was doing this final, I wouldn't even do it for Calc 1 because I know it's going to be a big Calc 2 thing anyway. So anyway, the answer to this is 1 over a, and it's arctangent or inverse tangent if you prefer, x over a plus c. If you look at you know, the formula sheets I've given you, if you look back in the chapter 5 stuff, that's a formula in the notes that you have. Okay, so what you do on this is actually pretty easy. This number 5 would be the integral of 1 over x squared plus 2 squared. Okay, now take the formula and you got the answer. So a is 2. So you would say 1 over a or 1 over 2 arctangent. And then it would be what? X over a, which is 2 plus c. That would be it. Now that's going to be, those who go into Calc 2, you'll do that all the time in Calc 2. It's one of the most common integrals you learn how to do. Okay? So that would be that. Okay? How about the next one? You can do this in your head once you catch on. 1 over 5, and then what? Arctangent x over 5. Good. Okay, so that's 1 over 5. Arctangent of x over 5 like that plus c. Okay? And that's another one that I haven't emphasized a lot, so I just felt like I probably ought to review that for that reason. Okay? We've seen it before, but not much. Okay, is everybody okay with that? So the integrals that you want to kind of study, you know, that I wanted to point out on this sheet were U-sub. We won't tell you when it's U-sub. Be sure you know this formula right here. That's real important because if you don't know that, you aren't going to get an integral that has that in there. And trig integrals always try to manipulate with basic identities. If you see something with trig functions in an integral, try that approach. Okay? All right, any questions about what I did? Okay? All right, this one, I think there's some of these on the final exam review that I provided for you, which we're going to go over a lot of those problems second half of class. But I want to just remind you of this. So what you're asked to do is find the slope of the curve of this function at the point 1, 1. Okay, how do you find a slope of a curve? You find the derivative, right? Okay, by now you better know that, if anything, from Calc 1. That's what a derivative is. How do you do the derivative of something like that? What's that? Implicit differentiation. Okay? And the thing is, if you were going to do this derivative, your choices would be solve for y before you do the derivative, but that's too difficult. Remember, if it's difficult to solve for y, you want to do implicit differentiation. Okay? So let's go through this and kind of review the implicit differentiation. That's something you want to definitely know how to do, is how to do implicit differentiation. So what we do is we're going to do the derivative of both sides of this equation. Okay? And we're doing the derivative with respect to x. Okay? If we had this solved for y, we'd be doing the derivative with respect to x. So I'm going to start the problem just by doing this part right here. We're going to take the derivative of the left side of the equation, and we're also going to do the derivative of the right side of the equation, okay? And this is a pretty good one. I mean, I think the one that I saw in the final had some similarities to this. It's not super straightforward. There's quite a bit that you have to think about in this, okay? First thing you're going to do is do the derivative of xy. How do you do that? What kind of rule? Product rule. You have to. A lot of times students think it's the number in front of x, so it's y, or something like that. No. It's two functions multiplied, so you have no choice but to use the product rule. Okay, so we're just going to focus on that. So we're going to do the first, and you guys, a lot of you do the product rule backwards of what I do. Whatever you want to do. So I do the first derivative of second is what? dy over dx. Remember, you got to have dy over dx in your problem. Okay, and then backwards. The second is y. What's the derivative of x? 1. Okay, and you can do that in your head. So it's just the first times derivative of second plus second times derivative of first. Okay, now we're going to move on. We got the plus sign like this. Okay, now we're going to do this. How do you do that? Product rule again. It does have a chain rule in it too, it looks like. So what you're going to do with this is the same thing. We're going to do first x to the 3/2, and then we're going to do times the derivative of the second. Okay, doing the derivative of that is a power rule. So that would be negative 1/2 y to the negative 3/2 because you subtract 1. But what else? Yeah, how do you know to do dy over dx? Variables don't match. If you're doing a derivative with respect to x of y, variables don't match, so that's why you have to have that dy over dx in there. Okay? Then you do it backwards. You do the second, which is y to the negative 1/2. And then we do the derivative of the first, which would just be 3/2 x to the 1/2. Do you need dy over dx? No, because the variables match. Okay? And then what's the derivative of the right side? That'd be 0. Okay, so that's it. Now, it's a product rule. Okay, so you got to watch and be careful about that. Now, what I'm going to do in my next step is I'm just going to clean this up probably a little bit here. So I've basically got x. I'm going to write this as x. Whoops, I can't do that. I'm going to write this as x times dy over dx plus y. Then over here, this part right here that I'm circling there, I'm just going to write that as minus 1/2 x to the 3/2 y to the negative 3/2 times dy over dx. Okay, and then this third part right here, I'm going to write that as plus 3/2. And it doesn't matter what order you put this in. I'm just going to put x to the 1/2, y to the negative 1/2 equals 0. Okay, so we got that. All right, now you got to be careful about your implicit differentiation. What else do you have to do? Yeah, you got to solve this equation for what? dy over dx. That's what you want by itself. Remember, you want the answer to say dy over dx equals a bunch of stuff, okay? So what I'm going to do is this part right here does not have a dy over dx in it, so move it to the other side. Okay, and you can skip a few of these steps. I'm just going to kind of write steps real carefully on this. So I have x times dy over dx plus y, and that should be a dy over dx, minus 1/2 x to the 3/2 y to the negative 3/2 times dy over dx, and then that's equal to negative 3/2 x to the 1/2 y to the negative 1/2 like that. Okay, now what do I need to do? Factor. Okay, you got to factor. Okay, because you got to get those dy over dx's together. So that's a common factor. Factor it out. Okay, so if we do that, we're going to have dy over dx times, and that would leave us with an x there. Oh, hold on. Is that a plus y all by itself? It is. So what do I need to do with that? I need to move that also. Okay, so I didn't catch that thing being all by itself. So up here, what you'd want to do is move that over. Sorry about that. So here's what I'm going to do. I'll pause here and kind of correct myself there. I just didn't see that. So with that minus y here, what I should have done was before I factor, I need to move this part, the two parts that I have in red, move those to the other side. Okay? Now we can factor that out, so we would have x minus 1/2, x to the 3/2, y to the negative 3/2 is equal to this then. This is a messy problem. I knew this was going to be a messy problem. Okay, so we got that. All right, now what? Divide both sides by that thing. Okay, all right. So I'm going to do that. So we've got x minus 1/2, x to the 3/2, y to the negative 3/2 on that side. And you can kind of bypass that step if you want to and just do this in your head. So that's x minus 1/2, x to the 3/2, and then y to the negative 3/2 like that. Okay, we got what dy over dx is, though, but we still got a lot to do. So, what are we doing? I gave you the point 1, 1, so what do? I'm lucky we put 1, 1, because that'll make this easy, okay? Because it's easy to work with 1, so what do? Just plug it in. Okay, so x is 1, y is 1, so what you want to do is just on this one, everywhere you see x, everywhere you see y, put in a 1. So you'd have negative 3/2 times 1 to the 1/2 times 1 to the negative 1/2 minus 1. And then at the bottom it looks like you have x, which is 1, minus 1/2, 1 to the 3/2, and then 1 to the negative 3/2 like that. Okay, so thankfully I gave you a 1, okay? So what's 1 to any power? 1, okay? So you don't need to do square roots and stuff like that. It's just everywhere you see this 1 to a power, those things are all 1. So you would have negative 3/2 times 1 minus 1 over 1 minus 1/2 times 1 times 1. And you can do that in your head if you want to. So that would end up giving you, it looks like, negative 3/2 minus 1 over 1 minus 1/2. And then you just put that together. Now, there's more than one way to do this. You can get a common denominator if you want to. The way I would do this is a complex fraction. So if I multiply the top and bottom by 2, I get rid of the fraction. Okay. Otherwise, you can just do negative 3/2 minus 2/2, getting common denominators. But if you do it this way, I think it's easier. So you would have, multiply that out. That'll cross the 2's out, leaving negative 3. That would be minus 2. The bottom, same way, 2 times 1 is 2. And when you multiply that out, that crosses the 2's out, giving 1. So it's negative 5 over 1, so it's negative 5. Okay, the problem that's on the final may not quite be this complicated, but it's fairly similar. That one's just messy, okay? But the thing on that is, a lot of times, without review, a lot of times students won't know how to do that derivative unless the teacher says, do implicit differentiation. From my experience, that's what I would see on this kind of a problem. Okay? You need to know to do implicit differentiation because it's a complicated problem that you can't solve for y. Okay, you guys understand that okay, you think? Okay, that's a pretty tough one to do without making a mistake. Okay, let's do this last page, and this will kind of give this supplemental handout I gave today. That'll kind of take care of this part of this then. So a couple of other things on here that I wanted to go through. Now this one, my review had, I think, a midpoint. You want to be prepared on the final exam to either do a Riemann midpoint, a left, or a right endpoint, okay? This thing is on the calculator part of the exam too. So on the calculator part of the exam, one of the problems you will do is a graph and then doing a Riemann sum, okay? Either 4, I can't remember, 4 subintervals or 8, I don't remember. If it's 8, that's just a little more tedious and time consuming. So I'm going to do this one with 4. Okay, so you would be able to do this with the help of your graphing calculator too on this one. So I'm going to do this graph on here without the graphing calculator. It's really not necessary to do that. So what I'm going to do here is we're going to start by just doing a graph of, we're going to do y equals 2 cosine x, and we're going to graph that from 0 to 2 pi. And the The problem on the final may already have the graph. I don't remember. It seems like it already had the graph on there. So if we do this, you could do this with the graphing calculator. I'm going to go ahead on this one and just get this set up. We're going to go out to 2 pi. And then I'm going to just kind of go by 90-degree increments that are like on a unit circle. So we have pi over 2, pi, 3 pi over 2. What does that 2 do to the cosine? It's an amplitude change, so everything kind of stretches. Cosine starts at 1, but this is going to stretch up to 2. So I'm going to basically just go all the way up to 2 and then all the way down to -2 like this. Okay, so I'm going to go ahead and just get the graph here. So you would have your first point would be this. Then that would go to the x-intercept down to the minimum like that. Okay, and again, you would be able, if you needed to do a graph, you would be able to use your graphing calculator to assist you with that. Okay, so what we're going to do on this one is we're going to do these two things. We're going to do left Riemann sum, and we're going to have 4 subintervals. So what does the 4 subintervals mean? That means you're just going to do 4 rectangles. All right, so the way that you would probably want to start the problem, the first kind of key thing to do is find what delta x is. Okay, what's the formula for delta x? Because you need to know that. B minus a over n. Okay, be sure that you know that. Okay. All right, in this problem, what is b and what's a? Remember, that's just where you're starting from and where you're ending. What's that? 0 and 2 pi. So a is 0, b is that. What's n? 4. Okay, that's how many rectangles. Okay, so you want to know this. This is real important. So that would be just b is 2 pi, a is 0, n is 4. So you'd have 2 pi over 4. So that would be pi over 2. So what that essentially means is your base of your rectangles is pi over 2. And I've already got that kind of set up. So your first rectangle is going to be that base like that. Every time pi over 2 goes by, that's the width of your rectangle. Okay? Now let's set this up. Now remember, what I'm having you do on this is a left Riemann sum. You want to kind of review what the difference between left, right, and midpoint is. Okay? If you were doing a midpoint, then you would have to go further into this and get pi over 4. Okay? But you're doing a left endpoint. So that means that your first rectangle is going to start there. Then you're going to draw over and down like that. That's rectangle number 1. The height is the left endpoint. Okay? What if it was a right endpoint? What would this rectangle look like? It'd be nothing. It would just be a line, right? What if it was a midpoint? Then you go to pi over 4, and your rectangle would draw around the midpoint. Okay, that's the difference. Okay, does everybody remember that okay? Right? Because sometimes you're going to end up with something that's not even a rectangle. Okay, let's go to the next one. What we're going to do is this. That's what's going to happen on the next one, actually. So if you go to this next increment between here and there, the left endpoint is this. So what is this going to be?
0.
It's going to be nothing. Okay, it's a line. Okay, like that. Okay, the left endpoint tells you how high the rectangle is. In this case, the height is nothing. Okay, so that's how that goes. Now we go to the next thing. What's that going to look like? Same thing. The left endpoint is this thing again. So it's still nothing. Okay, like that. Now what's going to hold on. You go with this one, that's going to go down here. Okay, so the left endpoint goes down to the function, so you'll be here. Okay, that would be the height. So you're going to go straight down like this, straight over and up like that. Okay, so that would be that. Okay, so that next rectangle, and that's going to give you a negative value on that because it's below the x-axis. Okay, like that. All right. Now let's go to the next one. Okay, remember you're looking here and there. Left endpoint is this. So what's that going to look like? That's going to be nothing again. Right. Okay. That's the part sometimes that students struggle with a little bit. Is if you don't have a rectangle, that's actually a good thing. Okay, it makes it easy for you. Okay, so what you would end up doing on this is you essentially just need to find the area of each of these things. And you don't have to be all technical the way I was teaching you on this. You can just do this if you want to. This would be, you could call this region 1, region 2, region 3, region 4, and just crunch them out. So region 1 is just going to be base. times height. So the base is what? Pi over 2. What's the height? Well, the height would be 2. So that would take care of that. Okay, then if you go to region 2, it's still base times height. I've heard a lot of you say 0. Yeah, okay, the base is pi over 2, but the height is 0. So that's why it's equal to 0. Okay, so you don't even have a rectangle. And then region 3, this is where you got to be kind of careful about this. When you do base times height, the base is pi over 2. What's the height? Negative 2. Okay, you got to be careful about that negative because you're going to have a region below the x-axis, so it's going to provide a negative. Okay, then you go to R4. That's still base times height. So that would be the base is pi over 2. The height is 0. So that's what you do to get your answer to the problem. Okay, now what happens on this then is this is going to give you pi. This is going to give you negative pi. So the total area is going to be what on this problem? Okay, you may have suspected that from the beginning. I don't know, because if you have a sine or cosine, you do have some symmetry in that depending on where you're integrating from. Okay, so what would happen on this then would just be you'd have pi plus negative pi plus 0, so it's equal to 0. Okay, all right. Now, what if we did more and more subintervals on this? What if we did 1,000,000 subintervals? Do you think it'd make any difference? I suspect not. So that's kind of the idea. Now, that's how you would do a left Riemann sum. That's just kind of peculiar to that problem that it was symmetrical, that it had a 0 area to it. Okay? So is everybody clear between the difference between left, right, and midpoint? Well, I'm tell you, you're going to do one of the three, so you just need to be sure you're clear on that. Yeah?
I just don't understand why the R2 is 0.
Because it's a left endpoint. Okay? So what this means is you have two choices. Okay? If it's a left endpoint, that gives you the height, and that's already on the function. It's already on the function. Yes, it's already on the function. Therefore, that would mean the rectangle. See, the rectangle starts at the left endpoint. Like this one starts here and draws around like that because that's already on the curve. This one, if you go to this one, you're on this point. And on this one, you're on this point. So what you're doing is you're doing left endpoints right there. And then that gives you the height of each rectangle. So if you go here, that's already at 0. It already has a y value of 0. That's why there's not a rectangle. Now, what if you did a right endpoint on R2? Then you would go down here and draw your rectangle around like that. That's the idea. Does that make sense? So one thing you can always kind of do, if you're doing a left endpoint, just kind of, okay, focus on that, and that will be the heights that you're going to use. So the heights are going to be 2, 0, -2, and 0. If it's a right endpoint, your heights would be 0, -2, 0, and 2. Like that. Midpoints, you'd have to crunch it out from pi over 4 is what you'd have to do. Okay? Okay, let's do these last two problems and we'll take a break here. Okay? I wanted to mention this. On here, all right? Let me just ask you a question on this, okay? We've learned how to do this before. What do you think? I can just bring down the x and have 2 to the x minus 1. Is that it? No. Okay, no. There's a rule for this, okay? The power rule only works for if you have x to the n. Not something to the x, okay? It's a totally different rule. So that's wrong to do that. Now, if you did the derivative of x to the n, then you know that would just be bring down the n, subtract 1 from the exponent, okay? All right? Now, the way I look at this problem is like this. By now, everybody's got this down. I know for a fact. Derivative of e to the x is e to the x, right? This is almost the same. Instead of e to the x, it's 2 to the x. So do you remember what the answer is? Itself, and then one other thing. ln of 2. Okay? So anytime you have e to the x, see, it even works on this one. If you did the derivative of e to the x, technically it's itself times the derivative of e. That derivative of e is just 1. So it works like that. So if you encountered the derivative of 1/2 to the x, Well, that answer is 1/2 to the x, and then what? ln of a half. That's how that works out, okay? So that's just something to kind of pay attention to for some unknown reason. Okay, let's do this last one here, and then we'll take a break. Okay, now this is a kind of thing that we didn't emphasize very much in this class. That's the reason I want to go over this a little bit, is when you're doing a derivative of an integral. Well, the way to work this out is just do the integral. Just do your antiderivative, and then take the derivative like this. Okay, so I'm going to kind of do this like this then. Okay, so let's just kind of focus just on this part of the problem right here. Just this part right here. All right, what is the antiderivative of the cosine? It's the sine, right? What's the antiderivative of the sine? Negative cosine. Be careful about those negatives, okay? If you don't know, double check yourself. So what this would be is you would end up with, we still got the derivative, but the antiderivative is sine of t, and then you're going to evaluate that from 1 to negative x. Okay, now we can do that. We've learned how to do definite integrals, so you're going to do this like this. So when you bring this down, we're going to have the derivative of, okay, then you're going to do sine of negative x, plug in the upper limit, then plug in the lower limit, and then do the derivative. Okay, you with me so far? Antiderivative of cosine sine. Plug in evaluate your limits. Now we're going to do a derivative on this. Okay, and let's see what we get here. All right, what is the derivative of a sine of negative x? Be careful. What'd you say?
Negative sine x.
No. I like that you had the negative, but I don't like the sine. What's the derivative of sine? Cosine. There you go. So it's cosine of negative x, right? Then what? Times the derivative of what's inside. Like that, right? That's a chain rule. What's the derivative of sine of 1? 0. How come? It's a constant, right? The sine of some number is a constant, so that's 0. So what you'd end up getting is you would get negative cosine of negative x like that. What you're doing is you're doing an integral, and then you're taking the derivative of it. So what I want to show you is basically this idea here. What will happen is the answer was not quite the same because that was a negative x. Now, if that was an x and not a negative x, I'm going to do one that has an x on the next one, then it would be the same. Anytime you do the derivative of an integral, it should give you back the same thing. The reason it didn't give the same is because of that negative. And everything was just off by a negative as a result. Now, you don't have to know that. You just need to crunch this problem out the way that I showed you. Okay, let's do this next one here. So we're doing derivative from 1 to x. Yeah, go ahead.
So cosine of negative x is the same as cosine of x, right? Because this cosine is
cosine is actually, it's an even function. So there is an identity that says this. It says basically the cosine of negative x is equal to cosine x. That's called, a cosine is an even function. So this thing could be written as negative cosine of x. So it's not the same, okay? That's kind of the key thing. It's not going to be the same. Okay, let's do this one. All right, what is the antiderivative of secant tangent? Secant, okay? So what we're going to have on this then is we still have our derivative. So we have the derivative of secant tangent from 1 to x. Okay, like that. All right. Now we're going to plug in that x. Okay, everywhere you see a t, you're going to plug in an x. Then you're going to plug in a 1, and then you'll have this. So you'll end up having d dx, and you'll have secant x, tangent x, like that, and then minus secant 1. Is this thing not working right? Secant of 1 times tangent of 1 like that. Okay, got the antiderivative, and now I plug in the x, plug in the 1, and subtract. Okay, yes?
Isn't the antiderivative just secant?
Oh, yeah. Why did I do that?
Secant tangent
Jeez, man. I'm ready for vacation. Jeez. Okay, yeah, that would just be secant, right? The integral of the secant tangent is secant, like that. Okay, that's better. Okay, that's what we should have. All right? Okay, now what we're going to do is we're going to do the derivative of, God, this thing is not writing dark on this like it used to. So let's see, this is going to be secant of x minus secant of 1. Okay, like that. Okay. Now, the point on this problem is what's the derivative of secant? Secant tangent. Okay? And what's the derivative of secant? 1. Yeah. Okay, did we go back to the beginning? Yeah, and the thing is, anytime you do a derivative, this is a part of what the fundamental theorem of calculus says. We didn't emphasize this a lot, is if you take the integral from 1 to x, you'll get the same thing back. But that other problem I did 1 to negative x, so you were off by a negative, okay? So that one right there, I mean, you could know that that's the answer on it. You could know that. If you go 1 to x, then that's always going to work. That's it, okay? All right, let's take a 10-minute break. When you come back, we'll kind of work on some of the other stuff that's in my review. But you want to make sure you get all this stuff down.